Laying down thousands of kilograms of hyperheated liquid metal introduces a catastrophic engineering challenge. It creates a massive, unstable thermal gradient. Without immediate intervention, the continuously accumulating heat would rapidly melt the underlying foundational layers. The entire massive structure would simply collapse, yielding under its own tremendous. Building a 100,000-ton supercarrier traditionally requires over 3 years of continuous labor. It demands the meticulous assembly of more than 300,000 individual plates of high-strength, low-alloy steel, known as HSLA. Furthermore, it requires hundreds of miles of manual and automated welding. However, in the brutal reality of naval warfare, every single weld seam represents a microscopic vulnerability, a microscopic point of failure against the devastating kinetic energy of a modern torpedo or the relentless, crushing hydraulic pressure of the open ocean. But what if we could completely eliminate the weld? What if a massive naval vessel is no longer assembled from thousands of fragmented pieces, but continuously extruded from a single monolithic block of liquid metal? Welcome to the ultimate paradigm shift in heavy naval architecture. Today, we dissect the mechanical anatomy of the world's first giga-scale additive manufacturing facility, a highly classified industrial complex specifically designed to 3D print the seamless hull of a nuclear-powered aircraft carrier. To understand the magnitude of this operation, we must first analyze the physical environment. This is not a standard, open-air shipyard exposed to the elements. This is a 400-meter-long, hyper-controlled environmental chamber, a facility so incredibly massive it operates its own internal autonomous rail network just to manage the relentless logistics of heavy raw material spools. The atmosphere inside this colossal hall is heavily scrubbed. It utilizes high-capacity industrial ventilation systems to maintain absolute climate control, preventing any airborne particulate contamination from compromising the structural integrity of the metal. The beating heart of this unprecedented manufacturing process relies on industrial scale. Wire Arc Additive Manufacturing, commonly referred to as WAM, operating in tandem with directed energy deposition or DED technologies. Suspended high above the reinforced concrete floor, moving along a high-precision multi-axis gantry system, is a synchronized swarm of 50 heavy-duty robotic arms. These are not your standard automotive assembly line robots. Each individual unit acts as an ultra-precise mobile foundry. Operating in absolute mechanical unison, these robotic systems maintain a continuous deposition rate of 15 kilograms of material per hour. They are engineered to feed heavy spools of naval-grade steel wire and Ti6L4V, an extreme environment aerospace-grade titanium alloy, directly into an intensely focused electric arc. The physics behind this deposition phase are extreme. The electrical arc generates localized temperatures exceeding 1,500 degrees Celsius, instantly liquefying the heavy alloy wire. As the heavy-duty robotic arm navigates its pre-programmed spatial coordinates, it deposits the molten metal layer by microscopic layer. Through this continuous, relentless extrusion, it forges a monolithic hull structure without a single structural joint. However, exposing 1,500-degree liquid metal to standard atmospheric oxygen would result in violent oxidation, rendering the alloy brittle and completely useless. To mitigate this critical chemical reaction, every single robotic deposition head is equipped with a localized gas shielding mechanism. It continuously pumps high-purity argon gas directly over the melt pool. This creates a localized, invisible, inert envelope, entirely isolating the vulnerable liquid metal from atmospheric corruption until it safely solidifies. Yet, laying down thousands of kilograms of hyperheated liquid metal introduces a catastrophic engineering challenge. It creates a massive, unstable thermal gradient. Without immediate intervention, the continuously accumulating heat would rapidly melt the underlying foundational layers. The entire massive structure would simply collapse, yielding under its own tremendous gravitational weight. The engineering solution to this critical threshold is an aggressively integrated, closed-loop thermal management system. Embedded deep within the massive load-bearing printing bed are hundreds of high-pressure liquid nitrogen cooling channels. These advanced channels dynamically regulate the precise solidification rate of the freshly deposited metallic layers. By extracting the extreme heat at a highly calculated, algorithmic velocity, the system ensures the optimal crystalline lattice formation within the steel. This precise thermal control guarantees that the structural integrity of the printed hull vastly exceeds the tensile strength of traditionally forged steel components. It is a masterpiece of thermodynamic engineering, scaling laboratory-grade material science to the size of a floating fortress. However, stabilizing the molten pool is only the first phase of this extreme manufacturing matrix. The true engineering nightmare of large-scale additive manufacturing is managing the violent forces of thermal distortion. As thousands of layers of 1,500-degree molten titanium and high-strength steel are continuously deposited, they undergo rapid continuous cycles of thermal expansion and subsequent aggressive contraction. In a structure of this immense scale, these unmanaged residual stresses would literally tear the hull apart from the inside out, inducing catastrophic structural warping and microscopic internal fracturing long before the vessel ever touches the water. To counteract this violent physical reality, the facility utilizes a highly automated, in-situ stress relief heat treatment protocol. Mounted directly behind the primary WAM deposition, heads are secondary, high-intensity induction heating coils. These electromagnetic coils continuously bathe the newly solidified metallic layers in a precisely calibrated thermal field, effectively annealing the metal in real time. By dynamically manipulating the thermodynamic cooling curve through continuous temperature feedback loops, the robotic systems forcibly realign the metallic grain structure. This controlled thermal soaking completely neutralizes the internal kinetic tension, ensuring the massive hull maintains absolute dimensional stability throughout the multi-month printing process. Simultaneously, the facility must address the surface finish. Wire Arc Additive Manufacturing leaves a distinct ribbed surface texture. To achieve the absolute hydrodynamic efficiency required for a nuclear supercarrier, the facility integrates a subtractive manufacturing phase. Following closely behind the deposition and heating arrays are heavy-duty, 5-axis CNC milling heads. These automated machining modules carve away the excess material with sub-millimeter precision, smoothing the hull's exterior to an exact aerodynamic and hydrodynamic profile, optimizing the vessel's drag coefficient for maximum fuel efficiency and velocity. Once the physical deposition and machining are complete, the structure enters the most ruthless, zero-tolerance quality control mechanism ever designed for naval architecture. Traditional visual inspections or basic manual ultrasonic scans are woefully inadequate for verifying a monolithic hull of this magnitude. Instead, the facility deploys a colossal automated non-destructive testing gantry. This system utilizes advanced phased array ultrasonic testing, or POUT, operating simultaneously with high-energy X-ray computed tomography. Massive robotic scanner arms sweep across every square millimeter of the newly forged hull surface. They pump multi-directional, high-frequency sound waves deep into the solid metal matrix, searching for the slightest acoustic anomaly. The X-ray CT systems, operating at a massive 9 mega-electron volts, generate enough penetrating radiation to see straight through 300 millimeters of solid steel composite, rendering a perfect three-dimensional digital twin of the internal atomic structure. These sensor arrays are hunting for microscopic porosity, unacceptable lack of fusion between the printed layers, or structural anomalies smaller than 0.1 millimeters in diameter. If the sensors detect a microscopic void, an automated high-precision laser ablation system is instantly deployed. It vaporizes the defective zone with a concentrated thermal blast, and the robotic WAM arms immediately redeposit flawless material into the cavity. This relentless feedback loop guarantees a mathematically perfect structural integrity. Entirely devoid of the internal weaknesses, inherently found in traditionally cast or welded steel sections. With the monolithic hull sections verified, the operation advances to the critical integration phase. A supercarrier is not merely an empty hydrodynamic shell. It must safely house a massive nuclear reactor complex. Mating the 3D printed hull modules with the internal nuclear propulsion compartments is a mechanical operation requiring absolute millimeter precision. Moving a 10,000-ton printed hull module requires extreme heavy lift logistics. The facility utilizes a synchronized grid of heavy-duty, multi-axle, self-propelled modular transporters, commonly known as SPMTs. Consisting of over 400 synchronized drive axles, these hydraulic platforms share real-time load distribution data to prevent any structural flexing. Guided by laser-assisted spatial positioning systems and GPS, these platforms maneuver the colossal hull sections into exact alignment. The physical tolerances here are unforgiving. A spatial misalignment of a single millimeter could fatally compromise the drive shaft geometry or rupture the heavily shielded nuclear containment bulkheads. The successful deployment of this giga-scale additive manufacturing matrix represents a total disruption of the global military-industrial complex. By shifting to this monolithic printing process, the facility completely bypasses the traditional, heavily fragmented global supply chain of raw steel parts, forged bulkheads, and cast components. It eliminates the logistical nightmare of transporting, storing, and tracking hundreds of thousands of individual metal plates across multiple continents. Furthermore, precision additive layering reduces high-value material waste by an astounding 40% compared to traditional subtractive manufacturing. But the true paradigm shift lies in the temporal metrics. This technological triumph breaks the physical limits of traditional naval construction. It drastically compresses the structural fabrication timeline of a 100,000-ton supercarrier hull from a standard 36 months down to an unprecedented 8 months. It is the ultimate manifestation of advanced heavy engineering, completely reshaping the future of maritime supremacy and global infrastructure through the raw, unyielding power of automated industrial manufacturing. To continue exploring the absolute bleeding edge of global engineering, and the hyper-advanced megaprojects shaping our industrial future, ensure you subscribe to the channel and activate the notification sequence.